Hello, these are the solutions to recitation activity 5. So which reaction absorbs heat and is hence endothermic? And so the process of absorbing heat is what we call endothermic. So that means the delta H, the enthalpy change of the reaction has to be greater than 0. That's the meaning of absorbing heat. That's endothermic. And so a process that absorbs heat is generally not a combustion reaction. These are reactions that produce a flame or an explosion. That's heat being given off. Those are exothermic reactions. The delta H of those reactions are negative, so less than 0. And then if you think about boiling water, so what's that reaction? If we write it out as a reaction, it would be water liquid, boiling, converting into the gaseous state. And so this process here has to have water absorb heat to break the forces that allow water to be a liquid or broken, so it then turns into water vapor. And so this reaction here should have a positive delta H. It turns out it's equal to about 44.0 kJs per mole. Not that you have to have that value memorized, but you could look it up and determine it, or maybe see it in some examples. Um, if you look at ice melting into liquid water is also endothermic for the same reason, that we have to take the cold ice, warm it up in order for it to melt. And so that tells us it's an endothermic reaction. And if you flip these reactions, then they're exothermic. So if you take the liquid water and need to freeze it, then you have to take energy out of the liquid water for it to cool down. In other words, you got to put it in the freezer. You got to put it from a warm environment into a cold environment so you can take the heat away. So you have to lose heat. So heat has to be lost. That's exothermic. And just like if you flip the water gas to liquid reaction around as well, that would become exothermic. If you go water gas to liquid, that would be exothermic. So only reaction 2 here is an endothermic reaction. Just to kind of piggyback off question 1 and to not flip back to question 1, but one other thought on question 1 would be that you can't just generally look at any random reaction and know if it's exothermic or endothermic, but phase changes we can tell the sign just from the nature of phase changes, what we know about them. And then if we know something about a reaction, like a combustion reaction takes place with that combustion, that flame, that explosion, we know that's heat being given off, that's energy being given off from that reaction. Okay, moving on to question 2, a chemical reaction that warms up its surroundings. So a reaction takes place and the surroundings of the reaction warms up. So I'd say the temperature of the surroundings increases. That must mean the heat of the surroundings increases, because temperature is just a measure of heat. So if temperature goes up, the heat of the surroundings goes up. And so what about the reaction that produced this change in the surroundings? A reaction that enables the surroundings to increase in temperature to increase in heat must have lost heat. So the reaction must be less than 0, must be negative. We have this relationship that the heat of the reaction is equal to the negative heat of the surroundings. So we know if the surroundings is positive, then the heat of the reaction must be negative. So the reaction is losing heat in this process here, and that's what we call an exothermic reaction. So the reaction is exothermic, and then the sign of delta H in Q reaction is that it should be negative, and then delta H is our Q reaction for our open system. So that's the connection between Q reaction and delta H. So the complete combustion of ethanol requires or proceeds as indicated below by this reaction. So ethanol plus O2 goes to CO2 and water. How much heat is absorbed or released when 2.5 moles of ethanol combusts? Well, a Q reaction here, or my delta H is less than 0, it's negative. So that means this is an exothermic reaction. So the reaction is releasing heat. So heat's going to be released by this reaction. If I go to calculate my Q reaction, I might take my 0.250 moles of ethanol. And then according to my balance equation, the Q reaction is minus 555 kJs per, and I look here, a 1 in front of methanol, that's per 1 mole of methanol, or excuse me, 1 mole of ethanol. And so I just multiply 0.25 by 0.555, or negative 555, that gives me 139 kilojoules. Now this is negative, and so this is the heat change of the reaction, And so the reaction's losing 139 kilojoules. And so that 139 kilojoules of heat is released by the reaction. And so if our Q reaction is positive, then heat would be absorbed by the reaction. If it's endothermic, heat's being absorbed. This reaction is exothermic, and it's heat being released. So this is an enthalpy, so we're told here if the enthalpy of ice to liquid water is plus 6.01 kilojoules, we mentioned on that earlier slide that solid to liquid phase change for water or any substance would require the cold substances in ice be warmed up. And so to heat up the substance is giving it energy to, giving it heat to go through the phase change process. So that's what we mean by an endothermic process. What is the enthalpy of this reaction though? And so this allows us to remind or to say that our delta H here, delta H of reaction, assumes that the coefficients in the reaction are moles. So when 1 mole of water solid converts to 1 mole of water liquid, then that reaction has a delta H of 6.01 kJs. You can think it's 0.601. It's plus 6.01 kJs per mole of water. So if I have 2 moles of water, converting to if I have 2 moles of liquid water, converting to 2 moles of ice, then first thing first, I flip the reaction, so the sign should flip. So if I flip the reaction, I flip the sign on delta H from positive to now negative. So this is an exothermic reaction, and I doubled the amount. And so I got to multiply this by 2. So this should be minus 12.0 kJs. So negative because I flipped the reaction. So if you flip the reaction precisely without changing the coefficients, it would be minus 6.01, and then times 2 to minus 12.0. Okay, so which statement is true for ammonium nitrate, which dissolved in water, or dissolves in water according to this equation here? So endothermic reaction, because delta H is greater than 0. And so when this reaction takes place, we should have the reaction absorb heat. And so the reaction absorbs the heat from the water, from the solution that's taking place in. And so the heat of our solution here should drop as this reaction takes place because the reaction's taking the heat away for it to take place. And so the heat of our reaction is positive, and then the solution needs to be the opposite of the sign. So if I have the reaction increasing its heat, then the solution must lose heat to make up for that. So the solution should drop in temperature because the reaction absorbs some of its heat. Answer B. Moving on to 6, would iron or aluminum of equal masses added to 100 degrees of water lead to a greater temperature change when added to the water at room temperature? And so we're placing, equal masses of either hot iron or hot aluminum into water. And so the key difference here is that the specific heat of aluminum is greater than that of iron. So, sometimes this is confusing, but if you think about heating up the piece of iron versus the aluminum might take longer to heat up to 100 degrees C, but eventually they reach 100 degrees C. I talked in class about how you can imagine taking maybe a test tube that just has a solid in it, and you place the test tube with the solid into a water bath. So you let the water heat up the test tube and therefore the metal inside of it. And so that's how you can create these metals at a temperature equal to the boiling of water. And it might take the aluminum longer to reach that temperature, but it has more heat to give. The aluminum has more heat to be released into the water, so it's going to increase the water temperature by a greater amount. And so it should be the aluminum that causes a greater temperature increase because aluminum has more heat to lose for an equal mass compared with iron. Iron has a lower specific heat, absorbed less heat to heat up, therefore has less heat to give to the water to heat up. You could run through an example if you really want to, and you could take a certain quantity of water, take like 100 grams of water, take 10 grams of each of those solids. We kind of did the example with iron in class, so we found specifically for the 10 grams of iron into, it was 100 grams of water, if I recall, that this item at 100 degrees C into 25.00 degrees C water increased the temperature to 25.8 degrees. Without running through the math, my guess is with double the specific heat for aluminum, my guess is it's going to increase that water from 25 up by about 1.6 degrees. So I bet if anybody wanted to double check the specific math for the specific quantity of 10 grams of aluminum, but my guess is it's going to work out to be about 26.6 degrees C. So it's going to be aluminum causing a greater temperature increase. And it's kind of crazy to think that you would put something hot into water and the temperature would drop. So neither one, of course, would lead to a temperature decrease. Question 7, we have a coffee cup calorimeter problem. So we have a calorimeter containing water. We're often given mass just to save us from converting volume into mass. You might wonder in these problems, why are we given mass of water? Well, it's going to be because later we need to use a Q is equal to MCS delta T equation where we need the mass of our solution. And so we're told we put some solid cesium chloride into the solution. We're told its molar mass, also at 25 degrees. So we have water at 25, the compound at 25. And then, of course, it's a water-soluble ionic compound, so it dissolves in the water, leading to a solution that then has a final temperature that's increased up to 32.82 degrees. And so the temperature of the solution increases, and that must mean that the heat of the solution increased, and that must mean that the heat of the reaction decreased. So the reaction loses heat in order to give the solution the heat that it receives to heat up. So our reaction here should be exothermic. And so we can calculate the heat of the reaction occurring inside the calorimeter. So the first thing we might calculate is our Q reaction inside the calorimeter, inside this coffee cup. And the way we're going to do that is that Q reaction should be negative Q of its surroundings. The surroundings is the solution. The solution is described by a negative MCS delta T, this being for the entire solution. And so I end up with an equation that looks like the negative mass of the solution, negative because of this negative relationship here, that the heat of the reaction is the opposite of the sign of its surroundings, the solution, and the mass of the solution. So I'm going to use the solution mass, so that's going to be these two masses summed together. So that's 162.5 grams times the specific heat of the solution, which we're told is 4.184 joules per gram degree C. So we're told to assume the specific heat of the solution is this number here, joules per gram degree C, and then I multiply by the delta T, final minus initial. So final 32.82 minus 25 degrees C is 7.82 degrees C. So my units cancel. And so I'm also going to do a quick conversion into kJs, so 1,000 joules per kilojoules, because we're told to calculate this Q reaction in kJs, and so I do this math here, so negative 162.5 times 4.184 times 7.82, divide by 1,000, go to kJ, so that's negative 5.32. So as long as we put the negative sign here, and it's always there, this has nothing to do with the reaction being exothermic. All Q reactions are negative Q of the surroundings. This is a fundamental relationship. And then our surroundings is the solution. So the surroundings of the reaction the solution is taking place in. And then we get the negative MCS delta T by keeping that negative sign in place. And then we just end up with a positive temperature change, or final minus the initial. So this is our TF minus TI. And so that just works out to be positive by the nature of the numbers, how they worked out. And so that, of course, makes sense with our Q reaction. We predicted, or we sort of thought it would be exothermic, and this, of course, is an exothermic number. Negative 5.32 is our Q reaction. But then the other question it's asking us is to determine the enthalpy of the solution process of the compound in kJs per mole. So if we think of our delta H of solution, the enthalpy of solution of the compound, that's this negative 5.32 number here, kJs, but that's per whatever the limiting reactant was, which was the compound. There's just one number to really choose from. It's like, do I put 12.5 grams of the compound? Do I put the water mass, or do I put the sum? Here, this is the heat that's released per amount of the reaction taking place. The reaction taking place is the cesium chloride, the solid, going into water and forming cesium plus and chloride minus. Like, this is the chemical reaction that's taking place. So what limits the reaction, if I do anything here, is I put that limiting reactant and that reaction in, and the limiting reactant, of course, is the cesium chloride, the only real reactant in the problem. And then I just convert it to moles. So I just multiply by 164.4 grams per mole of that compound. And that gives me the enthalpy of the solution process in units kJs per mole. So I just divide this by 12.5 and then multiply by 164.4 excuse me, 168.4 grams per mole, and I get negative 71.6. We could also ask you for the delta H of the solution reaction, which is 1 mole of cesium chloride in that reaction, so it would just be minus 71.6 kJs. All right, let's take a look at question 8. So question 8 is saying, can we somehow calculate the delta H of this reaction? So the following reaction we're told occurs in the stratosphere. Calculate the delta H of this reaction. Calculate the delta H in kJs for the above reaction using these provided reactions below. So the idea is, can I manipulate these reactions here? Can I take these reactions here and can I add them up, do whatever I need to do such that they sum up to our desired reaction here? And so hopefully we can do that. Now, the idea would be that if you think of A goes to B, and we did this example, the delta H for this reaction is, say, plus 20 kJs, and B to C is minus 40, then A to C would sum up to be equal to 20 minus 40 to minus 20 kJs. And so, but what if I told you instead of A to B versus B to C, what if I said, and gave you a reaction, instead of giving you A goes to B, what if I gave you instead, C goes to B, and that's plus 40? And then I give you A to B is plus 20. You have to know to like flip this reaction. If I flip the reaction to this one, then I flip the sign to minus 40. So the type of problems you see here with what we call Hess's law are problems where we're just trying to put like this puzzle together of how do I manipulate reactions so that they add up to my desired reaction. So what I might do is I might rewrite this reaction down to here and say I'm just trying to add up some of these, 3 reactions to sum up to OH plus Cl2 goes to HOCl plus Cl. I'm just inspecting. Everything's a gas. Again, we had the same issue in class where if everything's a gas, I'm just going to ignore writing the gas symbol for everything. And so how can we add these reactions up? Well, what I tend to do is I try to find something like, let's find HOCl. That's here. It's only in that one spot, but there's 2 of it. So I need to take this, third reaction here. I need to cut those coefficients in half. So right, a half H2O2 plus Cl goes to HOCl. The delta H of that reaction, and the reason why I have to note I got to cut those coefficients in half is I cut the delta H in half. So delta H is minus 209.0 times a half. Carefully. Okay, so then I look for another substance that's hopefully only in one of those reactions. Hydroxyl radical is one of those. So hydroxyl radical is a product, so I need to flip it to the reactant side. So I write 2 OH goes to H2O2. And if you're thinking already, it looks like I should cut that in half. You'd be right, but the delta H, let me flip the sign first. The delta H of this reaction would be negative 134.0 because I flipped it from the initial. And then I need to multiply this by a half because I have to cut the coefficient in half here as well. So I have the hydroxyl radical plus a half H2O2. And so you might think I'm done, but I'm not done because if I add these reactions up, they don't add up quite right just yet. It would be, OH plus Cl goes to HOCl if I add these up right now. So I need to do one more thing, and that is I need to have this chlorine atom here somehow turn into a Cl2. How do I do that? Well, that's what the first reaction's for. And so if I write that reaction as is, if I write Cl2 goes to 2Cl over here, notice that I now have chlorine on the proper side. So I have chlorine in my overall reaction. Then I'm going to sum up. So I add these reactions up. What do I get? And what cancels? What's on the same side in identical forms and identical amounts? So the things that are in identical amounts and identical forms are the H2O2, so that cancels out. And then one other thing that cancels out is one of the chlorines. So I have chlorine on one side, 2 on the other, so one of the 2 chlorines cancels. And so I'm left with the net. So what's net is Cl2 plus the OH goes to HOCl plus that remaining Cl atom, and that's our desired reaction. And so now I know I use that I use the first reaction that we'd been given exactly as is. I didn't make any changes to it. If you notice, it's still plus 242.0. And so now I just need to add up 242.0 plus 134 negative times a half, and then plus 0.5 times 209 negative, and I get plus 70.5. 70.5 kJ. So the idea is if you can add up these reactions, I'm just adding up reactions 1, 2, and 3 as I've re-edited them here, I can then add up their delta H's. So my delta H here was just the sum of delta H1 plus delta H2 plus delta H3. And so sometimes I write this delta H naught symbol. I just like to use that sometimes. This is just meaning the delta H of the balanced chemical equation of OH plus Cl2 goes to HOCl plus Cl. Question 9, we're given the standard enthalpies of formation of CO2 and water and their values. You can look these up in the back matter of the textbook for a lot of different substances. And so then we're asked to note the delta H of the combustion reaction of octane. We're then asked what is the standard enthalpy of formation of octane, the delta HF. So the standard enthalpy of formation is the delta HF. And the little standard symbol just means the little F symbol means formation enthalpy. If we take a step back and kind of think, well, what is a formation enthalpy? A formation enthalpy would be forming a compound, 1 mole of it, in whatever physical state it's going to exist in or we're considering, from its elements. So carbon's natural state is solid graphite. That's its most stable form. And then hydrogen's most stable form is H2 gas. And so we'd have, this is the balanced formation reaction. The delta H of this reaction is defining the standard enthalpy of formation of our compound, because the delta H of the reaction would be the delta HF of this guy minus 0 minus 0. Because elements in their standard state are defined to have 0 delta HF. So the delta HFs of these guys are defined to be 0. Okay, and so if we know how delta HFs work, the idea of them is that we can calculate a delta H of reaction by taking the sum of the delta HFs of the products minus the sum of the delta HFs of the reactants. And you have to take into account the stoichiometry of the products, it's called that N, and the stoichiometry of the reactants, it's called that M. So we're just taking into account how many of them we have. So what that means is I might write that I would have 8 times the delta HF of CO2. And so it's 8 times minus 393.5 kJs per mole. It's 8 moles times that, so that's where the mole unit's going. And then I'm summing up the product, so plus 9 moles of water times negative 285.83. The mole goes away, minus 1 mole times the delta HF of C8H18. The O2s are 0, and this all must be equal to minus 5471 kJs. And so we just do the math of solving this problem here. And if we take 8 times minus 393 plus 9 times minus 285.83. Let me do that real quick. So 8 times 393.5 negative plus 9 times 285.83 negative. That's negative 5720.04. I need to add that to both sides. So add that to negative 5471. So 5471 negative plus 5720 kJs per mole works out to be plus 249. So I have negative 1 mole of the compound times the delta HF of C8H18 equal to plus 249 kJ. So I just divide by -1 mole. Gives me the delta HF of CH18 is negative 249 kJs per mole. And so that's how we can relate standard enthalpies of formation. We use those to calculate delta H's of reaction by taking the sum of the products minus the reactants. If I know delta H, then I can solve for an unknown delta H in the reaction. Another key here to make sure we point this out is that delta HF of O2 is the standard state of oxygen, the element of oxygen that has a delta HF defined to be 0. Finally, for question 10, so the delta H of the below reaction can be approximated using bond enthalpies. The key here is, out of all the things in this chapter, this is the only topic that really is an approximation. It's not a direct calculation, but we can make an approximation for how much heat it takes to break the bonds in the reactants. So our delta H here is an approximation. So we approximate our delta H of reaction by taking the sum of the bonds. These is symbol for bond strengths we have to break, but in the reactants, and then minus the sum of the bond strengths of the products, of course, taking into account how many of the bonds there are. And so this is a weird delta that we're doing reactants minus products. And it's also weird in that it's an approximation, not a direct calculation. And then, because the idea is that we're taking averages of bond strengths in compounds that aren't always equal to these specific quantities. So this is just an averaging technique. And then also why it works for the reactants is the way you're doing this is you're trying to say how much heat does it take to break the bonds, then how much heat do I get back when I make my new bonds. That's why this process is working. And a bond strength is also like something like the NN triple bond going to two N fragments. The bond strength is a property of the reactant, not like delta HFs that was a property of the product. So it kind of flips the math, if you will. And so to convert N2 into 2N atoms, takes an absorption of plus 941 kJ. So heat's required to break bonds. So it takes heat to break these two bonds. It takes a lot more heat to break that triple bond in N2 than the single bond in the two hydrogens. But the energy it takes to break the two bonds here is 941 kJs per mole times the 1 mole of that bond, plus the 2 moles of the H2 times the 435 kJs per mole of that bond. So this is the energy it takes to break the bonds in the reactant. So 941 plus 435 times 2 is 1811 kJs. And then are the new bonds we're forming stronger or weaker? So I end up forming 4 bonds between nitrogen and hydrogen. So I form 4 of the NH bond. That's this value here. And then 1 nitrogen-nitrogen bond. So the NN bond is 1 mole times 159 kJs per mole. And so 4 times 389 plus that 1 mole times 159, that's 1715. So the way it works is it takes 1,811 kJs to break all those bonds in the reactants. Then I get back 1,715 kJs when I make the bonds, the new bonds in the products. So my predicted delta H is approximately equal to 1811 minus 1715, which is that's going to be plus 96 kJs. Terrible writing, apologies. But that's the plus 96 kJs that works out to. I'm just make sure, 1811 minus 1715. Yep, plus 96. And so, again, the whole idea here is calculate the energy it takes to break the bonds in the reactants and then sum up how much energy you get back when you make the new bonds in the products. If you want to see one more reason why this works, is it's just a Hess's law example of taking N2 plus the 2H2 into these fragments of 2N plus 4H atoms, that delta H is plus 1811 kJs to break those bonds. And then if you think of the energy it took to break the bonds of if we took the, um, the NH2 to break its bonds into the fragments of 2N plus 4H, to go from this side to this side was plus 1715. So to go from the atom fragments this direction, we flip that reaction. Now it's minus 1715 kJs. So 1811 minus 1715, the delta H for the combined reaction, which is N2 plus 2H2 going to this, has the delta H of plus 96 kJs. All right, so that's the recitation activity.